Let's spend a few moments discussing phase diagrams and showing you the pictures that result, the diagrams that we use in order to explain solid, liquid, and gas behavior. Various equilibria can exist in a substance between the liquid and vapor, between the liquid and the solid, and between the solid and the vapor. These are shown with phase diagrams. The phase diagram shows the behavior of the substance as a function of temperature here on the horizontal axis and pressure on the vertical axis. And all of the phase diagrams have the same general look. Solid appears above a certain pressure. Liquid occurs above a certain pressure and temperature, which we'll call the triple point, and gases occur above a certain temperature, and once you get to something called the critical point, at that temperature and above, the liquid stage cannot occur. We'll look at these in some detail. A graphical representation of conditions under which equilibria exist between the different phases of a substance. That's a good definition for a phase diagram. So given the temperature and pressure, phase diagrams let us predict what phase is stable or what equilibrium will exist. Let's use this diagram to illustrate. And we see three curves on the diagram. The curve we're most familiar with is the vapor pressure curve of the liquid, and as a function of temperature it shows the pressure at which temperature and pressure the liquid and gas will be in equilibrium, and as you can see it curves positively. Point C is the critical point. Above this temperature, the liquid cannot exist no matter how high the pressure is. The slope at point C is vertical as a result. Line AB, as you see here, is called the line of sublimation. Here, the solid is in equilibrium with the gas. Below it, you have only gas. Above it, you have only liquid. Line BD shows changes in the melting point as the pressure increases. And as you can see, for most solids, this solid is then denser than the liquid, the line tilting to the right. Let's examine some more points on the graph. First, and we're just going to choose a point now here up in the solid region, only solids can exist at this pressure and temperature. As we move to the right, we see at the same pressure but at higher temperature, both solid and liquid exist. This would be the melting temperature of this substance at that pressure. At point 3, the same pressure but a higher temperature, only liquid can exist. And finally, at point 4, at the same pressure but a higher temperature, both liquid and vapor exist. This would be the temperature above which you cannot get without turning it to a gas. This is the boiling point. And when the pressure is 1 atmosphere, this is the normal boiling point. And for water, that would be 100 degrees. We'll see something special about water momentarily. At a lower pressure, let's look at the various results. At point 5, only solid exists, even though the pressure is lower than it was back at point 1 a couple of slides ago. As we move to the right and increase the temperature, we get to point 6, which is called the triple point. Here, the solid is at equilibrium again with liquid, but both solid and liquid are in equilibrium with the vapor phase. You have all three phases in equilibrium at the same pressure and temperature. After that, any point 7 to the right of the triple point, you will only have the gas, the vapor, present at that pressure and at higher temperatures than at point B. Below the triple point pressure, you cannot have a liquid. Only solid, solid-gas equilibrium, or vapor phase is possible at the or below the triple point pressure. Now let's look at the special case of water. And you may remember that ice is less dense than liquid water. So in this case, we see that the solid-liquid line slants backwards, not forward, as it did in the general vapor pressure phase diagram. Looking also at the special case of carbon dioxide sublimes at 1 atmosphere pressure. Here's your 1 atmosphere pressure line, 101.3 kPa, and you can see that at 1 atmosphere pressure, the liquid simply does not exist at that pressure. Now, it is possible, even in the laboratory, to confine carbon dioxide solid, the dry ice, with the gas and let the pressure build up so that you actually see some liquid. This is possible in the lab. However, it should be done behind a protective glass because it is possible for an explosion to occur if the sublimation ruptures the vessel that it's being held in. Solid will not turn to liquid carbon dioxide at 1 atmosphere. If you have a carbon dioxide fire extinguisher, however, the pressure inside may be such that you actually can hear the liquid sloshing around inside. Finally, just for curiosity, water, when you get up in the 10 to the 3rd, 10 to the 6th, 10 to the 9th, 10 to the 12th atmosphere range, actually shows a total of 11 solid phases. This is something you can look up on the web or in very advanced textbooks. But when you can get very, very high pressures, you can get different kinds of ice.